Hello everyone, we will continue with our lecture series on this course, optimal control, guidance and estimation. So, up to last lecture we have talked estimation and then integrated design approaches, things like that, lot of advanced topics, what is happening in the research community at the moment actually. But then again in this next couple of lectures we will go back to the classical legacy material sort of thing, where we talk about various conceptual things in the textbook level basically. One thing that comes to mind is LQG design, okay, which is a linear quadratic Gaussian design. I have talked a little bit on that before, okay, but a little more systematically we will talk along with an example from a textbook also basically. Okay. And then we will also study something like neighboring optimal control, okay, which if you given a optimal path already, then how do you find out another optimal path which is close to that actually. Okay. So, that is neighboring optimal control, and then along with that sufficiency condition as well. Okay. And sufficiency conditions are classified in various categories like weak sense, strong sense, things like that. We will just summarize the results in the weak sense. In strong sense will lead this weak sense, if you really want to understand the details of this design, details of the analysis, then it talks a lot of mathematical tools and all that. So, we will try to avoid, but rather try to understand the summary of what the condition says actually. Okay. So, these materials are taken from these books. First thing is a classical book, as I told in my first lecture. This is one book which is heavily referred in a lot of papers actually, okay, probably the most referred book ever in control theory, entire control theory basically, okay. That is my guess. And some topics are also derived from Anderson and Moore, especially for linear quadratic methods. These are a very rigorous book. It talks a lot of this time domain as well as frequency domain analysis and all that. So, if somebody is interested, you can read that. Also, a little bit concept can be seen in optimal control estimation from Stengel. Okay. And also one small concept, some example problem that I will talk, I have taken from Frank Lewis book, and also I have not included that, but you can see that same thing in other books as well actually. Yeah. Anyway, so this first thing is this concept, robust control design through LQG concept actually, okay, linear quadratic Gaussian concept. So, this is very simple, okay. What we know in plant operation is we have a controller and we have output of various sensors and all, and we have been assuming that everything is available. So, we directly feed it actually, okay. So, we sort of kind of bypass this state estimation thing and then directly feed it to the controller and operate. Now, the question is, okay, outputs are noisy and also plant can have some process noise and all that. Now, the whole idea is how do we tolerate it or how do we design more and more robust control and all that is that way. So, the one idea that comes to mind is, okay, why don't you put an estimation in the loop, okay. You have a state feedback controller, that means control requires state information anyway, but in case of instead of directly measuring all the states or whatever, doing some algebraic manipulation from the output and feeding it back all the states which are noisy anyway, why don't we put an estimation in the loop which will not only filter out the output noises or sensor noises, will also try to kind of filter out the plant noises, okay. So, then you will feed that information to the controller and get a much better performance actually. So, that is the whole idea of how a controller is typically synthesized in practice. And this even if you think that, okay, I do not need I need to kind of design an estimation and things like the estimator, then it turns out that the sensors that you use, okay, typically they have their built-in estimators basically. The sensor output what you are getting in let us say inertial navigation system and things like that, they themselves have filters inside the instrumentation package basically. So, we do not see that explicitly and we do not have to really design it as long as you are concentrating on control part of it, but they are also part of the problem, part of the plant in general basically, part of the overall system basically, okay. So, without state estimation in the loop, probably the entire thing remains open loop actually in a way. In other words, if you really do not have any state estimation, you want to get away with that, then it may not work also, okay. So, this is as good as important as that what I mean actually, okay. So, if you really want to have a complete system, is either you have a built-in estimator which you typically do not see, or explicitly you have to design an estimator and then put it back into the controller actually, okay. So, That is how it will operate. Alright, so the philosophy of this LQG design is very simple in fact. It has two components. One is LQ controller, typically synthesized through LQR design, and there is LQ estimator, typically designed through Kalman filter. And here we talk on linear systems only. Okay. So, LQ controller and LQ estimator are everything actually. Okay, so and essentially when you there are various extensions of LQR as we know before, including some tracking problem and all that. So, this essentially gives us some sort of a good platform to have some fairly good robust control design in the loop sort of thing actually. Okay. So, bottom line is the controller is designed using LQR synthesis. The estimator is used, designed using Kalman filter synthesis actually. So, these two together and then you have got this design, that is called LQG essentially. Lot of other variations and all you will find in the book, but many books and different things, but essentially this is the key component actually. Okay. So, just to summarize the LQR design, we have studied that extensively before in a few lectures. So, you can see all those things if you have forgotten or want to revise. Then the performance index is like this, and if nobody tells us anything, we assume that TF is infinity. So, that means the cost function is quadratic in state and quadratic in control, and final time is infinity. And Q is positive semi-definite, where R is positive definite. Okay. And the system dynamics is linear, x dot is x plus bu, and the boundary condition is initial condition since it is known. Final condition since lambda f has to go to 0, and also if it is infinity time because of quadratic cost function, and all these conditions will guarantee that xf will go to 0, st goes to infinity actually. Okay. Alright, so this is the problem. Okay, and what is the solution? We have done the solution already, that control can be computed this way, essentially some sort of a gain matrix k times x with a negative sign u equal to minus kx, where k is computed as R inverse B transpose P. R is already R and Q are design parameters, tuning parameters, we already have it. So, R inverse we already have, B is the system dynamics matrix, so we already have from there. Okay. What you do not have is P, but P is computed as a solution of the Riccati equation, which is something like this. Okay. P A plus A transpose P minus P V R inverse B transpose P plus Q equal to 0. Okay. So, essentially you solve this Riccati equation, compute the P, then compute the gain matrix that way R inverse B transpose P, and you have a controller structure ready. The whole problem here is this x is not ready, your k is ready, but x is not ready, or even if it is ready, it is noisy. So, what do you do about that? Okay. So, then this idea comes to mind this technique comes to us very handy, that we also know well we have a way to kind of reject noise now. We know Kalman filter design, and which can tolerate both process noise as well as sensor noise. So, why not using that? Okay. So, the Kalman filter design summary in continuous time domain, other things are also there as a choice basically. So, in continuous time domain, what you say is x dot is x plus not only x plus bu, but you also have a gw component, and the output is not only cx, but there is a v component also. So, x dot is that way and y is that way. So, these are assumed to be white noise, and q is expected value of w transpose, process noise covariance, and r is expected value of v transpose, which is sensor noise covariance. Okay. So, q and r are typically process and sensor noise covariances. R is known from experiments and all that with respect to a particular sensor set that you are using, and Q is typically a tuning parameter, where the whole idea is to assume some sort of a larger Q. In the sense, it also tolerates the modeling inaccuracies on that. Whatever is inaccurate in the modeling part, it will come and sit as the noise basically. Okay. So, these are all we discussed before in detail. Okay. So, we have this, and then we talk about estimating the state using this sensor output information actually. How do you do that? You initialize some state to some values and then solve the Riccati, the filter Riccati equation as a filter algebraic Riccati equation, which is slightly different from what we see in the control Riccati equation. Okay. This is the one. Once you solve that, your P matrix will be ready, and then gain Ke can be computed as PC transpose R inverse actually. Okay. And detailed derivation and all we have already done much, so one of the previous lectures actually. Okay. So, we compute the gain that way, And once you compute the gain, we have an observer dynamics, okay. And this observer dynamics talks about a little bit innovation component, which is actual output minus predicted output, and then you multiply that with KE and then operate this filter with this initial condition. If you operate this observer dynamics with this initial condition. And the whole idea is as time goes, that means as time evolves, your x hat will converge to real x actually, okay. So, that means estimation is guaranteed to work as far as it is, as long as it is a linear equation by the way. So, the LQG design talks about fusing these two, okay. It talks about design and deterministic LQR control, okay. Forget everything about estimation design at this point of time, do not worry about it at all actually, okay. So, it assumes the perfect knowledge of the state and it assumes that plot is not affected by process and sensor noise. So, do not worry about that at all actually. Then you design a Kalman filter in parallel and do not worry about how this control is designed. This control gain, how it has come and all that, do not worry about that at all in estimation design problem, okay. You design that and find out x hat from this part of it and k from that part of it, and then fuse them together as u equal to minus k x hat now, is not k x, is k x hat. So, this design principle is called LQG, and the justification of LQG design comes from the fact that there is a big good theorem, separation principle, okay. So, these two things can be done separately and it does not affect the overall system. All these things by the way, remember that these are all valid only for linear systems actually, okay. The separation principle which is so nice, it does not hold good in linear systems in general. Nobody has proved that in a way. In other words, it is still an open problem, and some of you, if you really want to do some research in this, probably you pick up a nonlinear control design, various designs of course, and then also pick up something like a filtering design, either a E cap, U cap, H infinity filter or particle filter, whatever it is. You pick up a particular nonlinear filter and you did pick up a particular nonlinear controller and then try to see whether the separation principle is there or not. If you can prove that, the comment is it works in general, okay. We have seen that in previous lectures also, estimation operates in E cap and guidance and control operates in dynamic inversion, things like that. But nobody has come up with a proof for that and the rigorous confidence for that actually, okay. So, if you can take some of these problems and then come up with some ideas like that, then that will be a kind of path breaking sort of results actually, okay. Anyway, but coming back to this, so this separation principle was an idea of Kalman and his co-workers, and we tell okay, these two things can be done separately, okay. While doing one, other one we can ignore, but finally we can operate the control based on this, and this operates on separation principle. So, what is the separation principle? Okay, this has various proofs actually. Separation theorem can be derived in various ways, but a very quick way is something like this. We have the system dynamics, okay, x dot is x plus pu plus gw, but remember u is now minus kx hat, right. U is minus kx hat, okay. Alright, so this is what it is actually. So, if you put it back, this u is something like x equal to minus bk into x hat, okay, minus kx hat comes from here, okay. Alright, so this term is because of u. Now, if you see these two quantities, okay, alright, if you see these two quantities, then this quantity when x can be retained here, and then this is something like x hat I can represent as something like x minus x tilde, okay, right, because okay, this one x minus x tilde, okay, is actually x hat, right. Means our original state, remember, it is estimated state plus error in the state, okay. So, that is why this gives us that actually, okay. Alright, so this one is put here bk into x minus x tilde, and then this part a minus, now you can see that these two can be combined, x is happening here and here also. So, these two can be combined here like that, the rest one is bk times x tilde here and zw here. Okay. So, the error dynamics in Kalman filter, I mean in a closed loop, okay, right, error dynamics, well, not in the Kalman filter, but in the closed loop operation really. Sorry, the error dynamics in the Kalman filter, we have derived it like that. Okay. If you see the derivation of Kalman filter is something like x tilde dot is a minus k c into x tilde plus this time. Then remember we have got the solution for this, and then consider this as something like a time varying input, and this convolution integral blah blah, all these big derivations we had done before actually. So, essentially this is error dynamics in the Kalman filter. Okay. So, this is the system dynamics and this is the error dynamics. Okay. Now, the question is, can we not see them together? Remember, the error dynamics contains the information of the filter dynamics also basically. Okay. So, as long as we prove that the system dynamics and error dynamics are separate, then we are also done, okay, because one is dependent on the other actually. Okay. Right. So, whether we see that, okay, whether the actual system dynamics, okay, or the estimated state dynamics, okay, that those things are separate, or this is equivalently telling that system dynamics and the error dynamics, whatever I am saying x tilde dot, if it is separate, then x hat also is separate because of this relationship anyway. Okay. Alright, so to see that thing, okay, we put them together now. X dot and x tilde dot. So, x dot and x tilde dot. Okay. Now, this one, this a minus bk times x, a minus bk times x here, plus bk times x tilde. So, bk times x tilde plus zw external input, something like this, and x tilde dot happens to be a function of x tilde only and plus some external input. Okay. And when we talk about stability of the system, okay, we typically do not worry about the exogenous input. Okay. So, this time varying input to the system is ignored, we want to worry about the system matrix only. So, this matrix actually. Okay. So, x dot and x tilde dot is this here, and this part operates like that. Okay. So, if you see the expected value of the error dynamics now, because everything happens, these are all random white noise and all that, remember that. Okay. So, we can't talk about this dynamics per se, but remember these are zero mean white noise and all. So, if you take expected value of that, okay, this is nothing but expected value will come here, because this is a constant matrix. Remember these are time invariant linear system, LTI system. So, this is a constant matrix actually. So, expected value will come directly here, because it is a linear operator. Okay. So, you take expected value of that, this matrix times expected value of that, plus this expected value of this quantity. Okay. But this expected value of this quantity, okay, now you take if you see that this is essentially zero mean white noise, both W and V. So, if your expected value will go here, and all these things will be 0. So, this is as if it is not there actually. Yeah, this quantity happens to be 0 actually. Okay. Now, if you take dy dt of this one, this is, remember these are dots actually. So, essentially it talks about dy dt, this is written as the same thing, x dot and x tilde dot. So, dy dt of that essentially happens to be like that, because this component goes to 0 actually. Okay. Now, what happens to this dynamics, at least in the expected value sense. So, to analyze that, we can have this eigenvalue analysis, and eigenvalue of this matrix is determined by the characteristic determinant actually. Okay. So, the characteristic equation is given by this matrix determinant Si minus this matrix, this whole determinant, and that determinant you can now Si is a diagonal matrix, remember that. So, in a smaller sense, this I is different from this I dimension wise, remember that. This I is larger dimension, but this I is smaller dimension, this is also smaller dimension actually. Okay. But having said that, this small discrepancy, then this one can be written as something like this, because this is typically a diagonal matrix. Okay. So, part of that is put here, part of that is put here. Then this determinant is, if you take a partition matrix sort of thing and try to evaluate, okay, this partition matrix sort of thing and try to evaluate. Okay. Then this is nothing but the determinant of this okay, times the determinant of that minus 0 actually. This entire submatrix will become 0 because of that. Okay. So, essentially it talks about determinant of this is nothing but determinant of that into determinant of that. So, that is equal to 0, remember that we are constructing a characteristic equation to find out the eigenvalues. So, that has to go to 0, and essentially you can see now this is a scalar quantity and this is scalar quantity. So, both are determinant A times B sort of thing, it has to be equal to 0. That means either this is 0 or that is 0. Okay. That means, if this is 0, these are eigenvalues of the controller or closed loop control plan. If that is 0, this is eigenvalue of the aerodynamics actually. Okay. Now, the thing is the both controller and observers are designed in a good way. We have proven that also. So, the control is designed, the gain is designed in such a way that it results in a stable closed loop system dynamics. So, that means these eigenvalues are all in the left half plane, and also same thing for the filter dynamics, filter error goes to 0 ultimately. So, that means I mean expected value sense. So, that means these eigenvalues are also good actually. And the combined eigenvalues, it talks all that this particular result shows us that the poles of the systems or the combined eigenvalues of the entire dynamics are nothing but the poles of the controller and poles of the filter, because this one will result in poles of the controller and this one result in poles of the filter. Okay. So, essentially the whole I mean the poles of this entire system consist of nothing but the poles of the controller and poles of the filter, and hence the controller and filter can be designed separately actually. Okay. Even if you consider this and that separately, the combined system does not go bad actually. Okay. So, this is the separation theorem in LQG design. It is a big achievement because that gives lot of confidence to the people working on this domain that okay, things can never go wrong. Okay, if I implement that way, of course, provided both happen in the framework of a linear time invariant system. A small comment, we have also seen and many people have implemented Kalman filter in nonlinear framework, because that is the way to implement an EKF actually essentially. So, even if the controller happens to be in the linear framework, the estimator always happens to be in the nonlinear framework typically. And even controller, even if you design in a linear setting, linear system setting, typically the implementation will talk about at least some sort of gain scheduling. Okay. Gains will be interpolated, they are time varying actually. So, that sense it is also a nonlinear control design. And in that setup, many success results have been reported. You do not have to doubt or I mean you do not have to get afraid about that. But the fact of the matter is something like separation theorem is not there. Okay. So, it just bear that in mind actually. Alright, next we will see a small example to have a confidence actually. So, this is a short period control using LQG design. This is one of the design especially has been used extensively in aerospace industry also. Remember these things can be computationally not taxing actually. All that you are talking is just solve two Rickard equation, one filter Rickard equation, one control Rickard equation. And if it is it can be done offline, you compute the gains offline and this control gain offline and filter gain offline also, and then try to interpolate online. So, these things I find heavy use in industry also basically, including aerospace industry. So, one of the use is how to kind of do gust elevation, and that talks about short period control using LQG design. And remember, the short period is typically excited because of the gust, and those of you who have flown in aircraft might have repeatedly encountered this experience. They call turbulence and all that. Turbulence is there is tightening of your seat belt and things like that they will tell. Because those are typically the things when there is some wind gust actually, which will affect the dynamics little bit. The aircraft will vibrate for a little small time and all that. These are short period dynamics actually. Okay. So, pilot does not have to do anything. The control phenomenon, this autopilot design or the way it is implemented in aircrafts will automatically take care of that actually. Alright, so how does it operate? Let us see a small example problem here. This is F16 longitudinal dynamics, and F16 is longitudinal dynamics can be about some operating point can be designed that way, I mean can be written that way, and the next dot is x plus b times delta E. The way to control that this longitudinal motion phenomenon is by deflecting appropriate delta E to suppress that noise, I mean that oscillatory behavior. So, the dynamics that you consider is alpha dot and q dot, rate, angle of attack rate and pitch rate, and this angle of attack rate and pitch rate is strongly coupled with delta E, elevator deflection, and the dynamics happens to be about some operating point happens to be like this, where A and B matrix are given like that. Okay. All right. Okay. Now, G matrix is also kind of modulated, it's kind of identified that way. So, anytime there is a white noise sort of gust here coming, actually need not necessarily be white noise, any noise that comes here that gets influenced and the system dynamics gets influenced by this noise through this G matrix. Okay. At this point of time, it does not matter whether it is white or not, actually. Essentially, this is a wind gust phenomena, which is non-white also, basically, by the way. Okay. So, the moment there is a noise, there is a noise influence matrix, and that x dot will be put out like that. The moment there is a control reflection, there is a control influence matrix that will also alter x dot. So, if we compute this delta E properly, then this effect can be cancelled out, actually. But also remember, exact noise number and all will not be available. So, knowing one idea is, okay, why don't you directly cancel it algebraically? Simply not possible, because this number is not available. Okay. So, we have to estimate it, and estimation takes time, a small amount of time at least, and then based on that we can have a control design to filter out this one. But before we do that, okay, this alpha is angle of attack. Okay. So, typically the angle between body axis and velocity vector in pitch plane, and then q is pitch rate, delta is elevated reflection, wg is vertical component of the wing gust, actually. Okay, and those of you who do not know, I still suggest that you go back to my flight dynamics lecture as part of this course itself. Some of the early lectures in flight dynamics will give you some definitions like this and all that, actually, or you can see a flight dynamics books also. Now, what happens is, this is as I told, this wind gust is not white. So, how do you handle that? Kalman filter only talks about white noise. So, this is the way to handle, is something like a subsystem sort of thing, which will be modeled as this system dynamics and this output equation together, and essentially it comes through a transfer function realization. Actually, we have something like a transfer function, okay, which with this transfer function, okay, will take white noise. What happened here? Okay, this transfer function will take white noise and it will give non-white noise. Okay, so this means this will give W, whereas your WG is wind gust really, and this WG is the one which will go and affect the system dynamics, actually. Okay, remember, this is WG gust component, actually. Okay, so this transfer function, if you realize through a system state space realization, it turns out to be like that. And because it is a filter dynamics filtering problem or estimation problem, this observable canonical form is the one which is recommended here. Okay, remember, there are various forms of realizing a transfer function, that is not unique. In other words, if you know a state equation, realizing a transfer function is unique, but whereas if you know a transfer function, realizing that in a state space is not unique. Various ways exist, and because it is a estimation problem, the recommendation is you realize that in an observable canonical form. So, you do that, and then this AW and VW, all that will come into picture. So, now what you tell is, okay, I have got a system dynamics, okay, but there is a wind gust dynamics, which is represented as this system dynamics. So, I will put them together now. X dot comes from here and the Z dot comes from this part of the story, and then I will put them together here. Now, what happens? This W what we are talking here or here is essentially a white noise. That means, we can apply Kalman filter to this system dynamics, not to this system dynamics, okay, because this is not a white noise. So, this way of doing things is something called shaping filter and all that, and that is what this transfer function will be identified for this particular purpose, to model the wind gust phenomenon. This modeling is something like, if you take a white noise, pass it through this model, it will give you that particular noise which is physically happening, basically. Okay, so that is what is called a shaping filter area and all that, actually. Okay. And also, after getting this delta E, it has also passed through some sort of actuator dynamics, and actuator dynamics for control, this elevator deflection is a first order system with this transfer function, actually. Okay. All right. So, this is what it is. Then ultimately, This realization of that can be done separately or together. There are both ways of doing that. And if you do hard coupling sort of thing, that also will come into picture. Okay, this can be realized as a first order state space equation. And then you directly put into this here and tell, okay, I have got two system dynamics alpha dot q dot. Then these are the Quinn-Gust dynamics realization. This part will come here, and delta E dot is my actuator dynamics. I will put it there also. So I will directly compute the input to the actuator, okay, through this 5 state formulation actually. Okay. So even though it started with 2 states, eventually it will ended up with some sort of 6 states actually. Okay. Sometimes again I repeat, sometimes this is not preferable, you just put it as 4 states, because this will also talk about realization of actuator state now, okay, this delta E, if you put it this way. Okay. Now for actuator state realization, we also need a sensor for that, and some actuators are equipped, and especially aircraft equipped actuator, if you talk about it is there, I mean delta information is available. But sometimes when it is not available, you cannot recover that from other states obviously. So, it is not a good idea to put it that way. Okay. But in this particular case, because it is F-16, which is I mean heavily equipped and expensive also and things like that, the sensor, the actuators are capable of giving us the information about the actual delta E basically. So, that is available. So, we can put it that way. Yeah. Alright, now what are the measured outputs in this particular case? We are assuming, we are not really assuming this delta E sort of thing, but what we are telling is, our aircraft is equipped with sufficient sensors in measuring 2 quantities only, and these 2 quantities are nothing but normal acceleration and pitch rate. Okay. So, the normal acceleration and pitch rate, this is assumed, this gyroscope will give, this accelerometer will give us normal acceleration, and this pitch rate will be given from the gyroscope actually. Okay. So, these 2 values are these 2 sensor outputs are available with us, and this can be represented like this. Okay. And normal acceleration, remember, has to be represented in the form of alpha and q. Remember that output equation should be a function of states only. So, nz is this is the model part of it, it is a function of alpha and q this way. Okay. So, using these numbers now, and I also strongly suggest that you repeat this exercise yourself. You do your own MATLAB coding or coding through Simulink or whatever it is actually, and you generate the results of this way. This will give you a lot of confidence actually. Okay. So, nz is given like this. Then the measurement noise covariance is something like this, R is designed that way and Q is sigma square, you can like 25. Alright. So, the controller design is based on LQR control design obviously, this talks about that. So, U U is what? U is the input to the actuator, remember that U. Okay. This U comes from since kind of realizing this transfer function in a state space. So, the input to the actuator, okay, is directly computed through this augmented state information, and for this you need a control of this Riccati matrix PLQR. PLQR is computed through the controller Riccati matrix thing sort of a solution basically. So, you solve the controller Riccati matrix, put it back here for the gain design, and you are ready with the LQR controller. What about the filter? Filter operates through this dynamics. So, you have this state equation, this output equation, and then you have this, this is now a white noise because of the gust modeling, and this is also a white noise sensor output actually. So, now you can use filter, I mean Kalman filter, and then controller can be computed this way on the way. Now, what are the results? Results you can see very good, alpha is getting suppressed, and then remember 20 seconds is not a very bad time, if you 15 seconds really, 15-20 seconds, not a very bad time as far as aircraft equations are concerned, especially if you are really concerned about commercial aircraft and all, it does not matter that much, and fighter aircraft performance is more. So, even if there is importance for performance is more, so even if it takes a little longer time to suppress this gust phenomenon, it is still tolerable actually. Okay. Now, this is alpha is and this is q. And remember, alpha is 1 order smoother than q. Okay, if you think about this dynamics of alpha dot and q dot. Okay, if you see this equation, alpha dot is a angle that talks about angle between 2 velocity vector components actually. Okay, so and then q is directly the pitch rate. So, pitch rate is more sensitive to the gust actually. It will so alpha is 1 order smoother than that. That effect is also visible here. Q is also going to 0. but there is a small residual error, it's very negligible residual error. The structural kind of damping and all that will take care of that. Structural aerodynamic damping will not let you have this actually. So, do not worry about this small chattering here, it is not, in reality it will not happen actually. But even if you see on the way, there are these small residual errors which are smoothened out in the alpha level actually. Okay. Whatever control in time, we are not chattering at all. Control will nicely operate on the estimated state, and estimated states are these two, and control will be operating like this. So, with this control, application of this control, we will be able to take alpha and q both to 0 actually. That is the message. So, this LQG design is kind of a popular technique to do this kind of control design actually. But there are problems of LQG design also. Okay, but main problem is loss of robustness of LQR. Remember, if you have full state information in the LQR design, at that point of time in that lecture I also told that typically if full state information is available error free, then LQR has good robustness. That means you have as good as something like infinity gain margin and up to 60° phase margin also basically. But all these things are gone the moment you put a LQG design. LQG does not guarantee that basically. Now, the whole idea is, can you do some modification of this gain computation K and also the control the filter Kalman gain Ke. Somehow the core point was down there actually. Okay. So, if you blindly select these numbers like diagonal and then work with that some time domain phenomenon like that, then this robustness considerations are ignored actually. So, we have to go to the frequency response characteristics, and from there we have to propose a design kind of tuning basket sort of thing. Cannot tune wherever you want to, but it will allow you some sort of a basket from which you can pick up your tuning values actually. So, that is called loop transfer recovery. Okay. So, that idea is called loop transfer recovery, and LQG, when somebody designs LQG, LTR cannot be ignored. You have to kind of either incorporate in the control design gain selection process directly, or at least you have to test your selection, whatever matrix Q and R you have selected, whether it passes through the LQR test conditions, LTR test conditions or not actually. So, it passes through and you are happy with and all that, and then LQG LTR is kind of a good design actually. Okay, then there are other ideas also. Then just remember that LQG LTR everything operates based on two phenomena. One is white noise, the other one is expected value. Okay, everything happens in the sense of expected value, that average value actually. Okay, average value does not give us good confidence, because momentarily some noise can be very high and then system can go unstable and things like that. For example, surge protection sort of ideas when you talk about electrical circuits, when there are surges, and that point of time the entire circuit breaks down actually. Okay, so that kind of consideration, those kind of problems motivated the idea of something like H infinity design. That means you expect the maximum noise and then try to have your design kind of safe for the maximum noise input actually. Okay, so I will not talk too much on that, those are subjects of robust control course and all actually. But sometimes H2, H infinity, all that are also called as optimal control extensions ideas actually. But those are in different ball game altogether. So, typically taught in a robust control course actually. So, let me not talk too much on that. Anybody interested in that, you can also read some of these robust control books actually. And one of the very readable book is probably a book from Masijowski, okay, who was a professor in Oxford University, UK basically. Alright, so that is that part of the story basically. So, LQR and then Kalman filters leads to LQG, and LQG has a little robustness problem. So, we kind of bring in this concept of LTR, which gives us a way of selecting this Q and R matrices and all that, which will give us some sort of robustness back actually. So, LQG LTR turns out to be a good practical design approach actually. Yeah. Alright, so this part of the story here, and then let us move on to the next topic of this lecture. The next topic is neighboring optimal control. Okay. So, it is kind of related to LQR, but not to, we are hunting out for a neighboring optimal solution in true sense actually. Okay. So, we are not interested in deviation killing per se, but we are talking about some finding out a neighboring optimal solution actually. Just to summarize again a little bit, we have a performance index in general. Remember, these are, we are back to the nonlinear domain. So, these are all happens in nonlinear framework now. So, the optimal, I mean the performance index to optimize is some terminal penalty and some path penalty sort of thing. Then there is a path constraint, okay. Then there are boundary conditions, and then we have this augmented performance index, which talks about this kind of thing, okay. So, remember there are at final time not only there is a soft constraint, but there is a hard constraint set of equations also. Okay, so, not only this has to be minimized, okay, this function whatever typically quadratic and things like that, but this constraint should also be met, and that too in a partial set. It cannot be the full state, all the states and all that. The dimension of the equation can be different from the number of states actually. Okay, so, this can be Q equation sort of thing. So, one idea is, okay, you have this augmented performance index phi of x, and then this nu transpose, this Locke variable nu, this one is brought in here, nu transpose psi, this operates in the penalty part of it here, and then this state equation which operates throughout the trajectory happens to latch on to that, and this turns out to be like that. Now, the Hamiltonian is a function something like that, and you derive all these necessary conditions. X dot is del s by del lambda, again f of x u, then co-state equation, then optimal control equation, boundary condition. Then the boundary condition, remember, will come from this full term. So, it is not only this term, but lambda f is this term plus that term. Okay, so that's also don't forget that actually. Now, here is a problem definition like this. What you are interested in? First, you are assuming that we have determined a control solution ut satisfying all necessary conditions, and then we have this. Now, let us consider something like a small perturbation in the external path produced by small perturbation in the initial state somehow, either because of gust or something that we did not understand in the process. Somehow it resulted in some sort of a delta x naught, and from there onwards we want to find out a different path actually, which is optimal. Okay, so this was so what happened is there was some small perturbation, okay, that produced a small perturbation in the initial state and a terminal condition d psi also, okay, whatever you are talking here. Now, the question is something like this: under what condition ut is guaranteed to be local optimum first of all, and then if it is there, then can we find a neighboring optimal solution in an efficient manner? Well, you can always think that as a new problem, okay, after this perturbation happens, and try to go back and resolve your 2-point boundary value problem, and then solve a new path actually. So, that is not an option here. Can we really do a little more efficient way, because we already have a optimal path close to it. So, can't we do a better job? Can't we find out a little more efficient manner? And then the third question, under what condition such a neighboring solution exists actually. Okay. So, there is another issue there. So, the detailed derivation can be found in Bryson and book. Here we are interested in delta square j bar, the second order variation actually. Okay. So, first of all, you note that the available control solution satisfies all the necessary conditions of optimality. That means first variation is 0, that is already there. What you are interested in, making sure that the second variation is also minimized and all that actually. So, you are interested in del square j bar, and del square j bar can be derived something like this. And remember, these are all Bryson and notation sort of thing now. So, this phi x x stands for del square phi by del x square. Okay. Similarly, this del h u x stands for del square h by del u del x, like that. Okay. So, this is the performance index. So, with respect to the perturbed equation dynamics or system dynamics, which can be given like this. Okay. So, this is the system dynamic, the cost function, and this is the perturbed state equation actually. Okay. Similarly, the derivation in the boundary condition, or the deviation in the boundary condition can also be written something like this actually. Okay. Delta x naught is specified and delta psi is also specified, because we know that the perturbation that happened we know actually. So, that is available. Okay. So, essentially the problem happens to be a linear quadratic regulator problem, okay, but with cross product term also basically. Okay. These terms, these are there, okay. These cross product terms will appear actually. Alright. So, the state equation is like this, and the co-state equation can be something like this. Okay. With respect to this cost function, remember that. Okay. You have to derive all that. So, delta lambda dot turns out to be like that, optimal control equation turns out to be like that, and boundary condition like this actually. Okay. Again, I suggest that you derive this yourself in pen and papers, you will have lot more understanding actually. Then optimal control equation is given like this, and the co-state equation is given like this. State and co-state together can be given like this, where A, B, C can be derived from this conditions to be like this actually. Okay. Because now remember B is a square matrix and B transpose happens to be B. Okay. If you talk reverse transpose and all that. So, this is a symmetric square matrix sort of thing actually. Okay. So, what you are doing is seek a solution for delta lambda and delta psi, because that is what is unknown here. So, delta lambda and delta psi in the form like this. Now, remember the whole idea of LQR is we seek a solution lambda as a function of x, lambda equal to p times x. Similarly, like that we have to seek a solution as delta lambda as a function of delta x and delta nu also. Okay. So, this one we seek a solution like this and like that. Okay. And then you can talk about this boundary conditions imposition and all, delta lambda f and delta psi f can be represented like this actually. Okay. Directly it can be derived from that and you can put it that way. Okay. So, this essentially gives us the final, suppose you kind of compare these two guys, because this is from assumption and this is from what you have derived and all that actually. Okay. So, like that. We put them together, this tells us that there is a delta xf component, there is a delta xf component. So, p at tf has to be this component at time tf, because all variations cannot be 0 and all that. So, and similarly rtf has to be like this, and this is same. So, we do not worry about that, but qtf happens to be 0, there is no delta nu here actually. Okay, so that happens to be 0. So, the three boundary conditions are known to us. Now, what about the differential equations? So, you go back and see the delta lambda dot and things like that, exactly similar to what we have done in LQR setting derivation sort of thing. And if you follow the similar steps, it turns out that this equation will result, and because the variations cannot go to 0 and all, we will have two equations, one the same or very similar to the Riccati equation that we already knew before, then there is an additional differential equation like this. Okay. So, this will all result in, okay, if you put it back all the things that we know, this will result in, okay, not sorry, this is two equations. Okay. Then the other equation, if you analyze I mean this equation delta x dot and all that actually will also result in some sort of equation like this, and these two equations if you analyze together, okay, then this will result in this equation. Remember this I mean r dot coming out of here and r dot coming out of here will be same actually. So, we have this p dot, r dot and q dot, and ptf, rtf and qtf are given known to us actually. So, these three differential equations and three final boundary conditions, again the idea is to propagate it backwards and then store it and use it and something like that. Then we are ready now with the solution, and finally d nu can be computed as initial condition value inverse sort of thing, and then d lambda 0 can be computed that way. Okay. And also there is a small point to note here that qt naught, okay, should not be singular, and if it happens to be singular, then this optimization problem is said to be abnormal, something wrong here actually. Okay. The problem is formulated well, then qt naught will not become singular actually. Okay. Alright. So, with that assumption, then you can formulate delta lambda 0, and then d nu also you can calculate, and finally du can be represented all this like that, and ultimately it will result in k1 times delta x and k2 times delta t. Okay. So, k2 of t times delta psi. So, that means delta u is a function of delta x and delta psi basically. That is what is our objective basically, right. We wanted to compute that delta u, so that you can add it to the nominal u that is available, and you can go ahead actually. Okay. So, in many problems it turns out that this is not critical, this is just a comment, a simplified way of implementing and all that. So, it turns out that this is not critical and hence is not imposed, and you assume that this is also positive semi-definite matrix and things like that. So, delta square j becomes like that. So, essentially it happens to be a LQR problem in cross product term, which you know how to get the solution. So, if this constraint is relaxed, okay, all this exercise what we did is not really required in a way, because we know how to solve this cross product cost function, and then we go ahead and solve it actually. Okay, and especially also remember that that Tf has to go to infinity. I mean that when Tf goes to infinity, this will not be there. Okay, that becomes even more simplified actually. Okay. Anyway, furthermore, this is what Tf goes to infinity and things like that. You can artificially increase the weights and do some engineering solution instead of going through all these mathematical things and all that. Okay, and you can also think about solving the algebraic equation online. Essentially, it goes to this SDRE formulation, which we have discussed before as well actually. Okay. Now, before ending this lecture, we will just touch upon this idea of sufficiency condition, and we have been must have been kind of curious enough because all the way we have been talking about necessary conditions, things like that. But what about sufficiency condition? And also remember, the sufficiency conditions are also for local optimum only. We are not talking about global at all here. But still, what are the sufficiency conditions after the necessary conditions are satisfied? So, there are two, just very quick summary, there are two ways of doing things. One is in weak sense, other in strong sense. When somebody talks about weak sense, we talk about variations of delta x and delta x dot, both are small. And in strong sense, only delta x is small, where delta x dot can be large. Okay. So, even if that can be guaranteed, then that is called strong sense, and if both happens to be small and still you guarantee the optimality, that is called weak sense. Okay. So, we talk a little bit summary of the weak sense. Strong sense, I will leave it to self reading actually. Okay. So, the theorem 1 tells something like that: existence of neighboring optimum path, this is the conditions. The neighboring optimum path exists in weak sense, okay, from T naught to T f, if the following conditions are satisfied, that the second derivative of Hamiltonian with respect to u del square h by del u square, that is guaranteed to be positive definite matrix all the time, that is called convexity condition. And then q has to be a negative definite matrix, okay, that is called normality condition. And this q, remember, is not the design q and all, we have actually come up with the q inverse and all this particular q. Okay. So, that q dot, the solution of that, this final condition and this differential equation, whatever turns out, that is q of t actually. Okay. And that q of t has to be negative definite matrix, that is called normality condition. And then this one, this matrix, what you see, P of t minus R q inverse R transpose has to be a finite, it cannot be infinity actually, that is called Jacobi condition. So, if the convexity condition, normality and Jacobi conditions are satisfied, okay, then you call then it guarantees that the neighboring optimum path exists actually. Okay. And essentially the condition 3, the Jacobi condition, also talks about there is no conjugate point on the optimal path. Now, conjugate point is something very simplistic sense. If somebody wants to understand something like this problem, you have something like a, let us say you talk about a sphere, okay, something like this kind of a sphere, okay, and let us say you start from point A to point B, okay, right, something like that actually, and then probably you go to kind of north minimum path from point A to point B via North Pole and all that actually. Okay, something like, okay, now at North Pole, okay, something like, wherever you go in this direction, okay, it turns out to be the equal distance actually, right, if you talk about a minimum length path sort of thing. So, that means there is no clarity of which direction to go after North Pole actually. Okay. There are several ideas there, several paths, infinity number of paths really, where you can go to the same distance and blend up with the same value actually of the distance travelled. So, that is like kind of a conjugate point, and this Jacobi condition tells that there cannot be a conjugate point on the way actually. Okay. Alright, so that is what it is, and the theorem 2 tells us a very simple way of extension of that really, okay, which tells us that okay, sufficiency condition is nothing but conditions of theorem 1 actually. Okay. If the conditions in theorem 1 along with the necessary conditions also, because sufficiency conditions do not mean too much, without necessary condition. So, we have necessary condition as well as sufficiency conditions, then it kind of guarantees some sort of sufficiency condition for the entire problem actually. Okay. That means conditions on theorem 1, these 1, 2, 3 conditions as well as the necessary conditions form a set of sufficiency conditions for a trajectory to be local minimum actually. Okay. So, more and more details and then more extension, you can see some resonant book and followed up with some mathematical optimal control books and all that to get more ideas on that. We will not talk, because this is typically a kind of engineering flavor, even though we talk to sometimes the theoretical details and all. We will not go to this mathematical optimal control analysis tools too much. So, here I will not venture out to this further ideas and things like that. I will like in strong sense and all, if somebody is very curious to see and things like that, you can always refer to Bryson and other books actually. So, that is what I thought. On the way, it is good to have some idea about neighboring optimal control and sufficiency condition, things like that. So, kind of summarize it, but again they are not extensive at all. Anybody interested can see, especially Bison and Root to start with, and then build on that actually. Alright, so this is what I wanted to cover in this lecture, but just before that, again let me summarize that this particular book is a very seminal book. You can see many of the things from this Bison and Root. Other things are also there, especially Stengel book is very readable. You can read many things and understand what is going on actually. And this is frequency domain concepts, something like LQG, LTR concepts and all. If you are more curious, you can see this book actually. Alright, so with that comment, let me stop here for this lecture. Thank you.